It is 11:11 now.
11.
Yeah, make a wish. I had this thing. I had this on the charger, and it's not charged.
What is that? What do you have to?
This is the microphone receiver, transmitter. No, that's the transmitter. Yeah, 11:11. Make a wish. So.
You going outside, right?
Yes, hopefully. So hopefully we'll. So I'm hoping to go ahead and get through with
5, 4.
at least halfway through 4. Cause I want to make sure we understand these, talk about these.
I'm gonna tell you right now. Can you just read the 2 most important things off these slides and do like an example so we can get through? Because we still gotta go through 5. And we gotta get the thing on Tuesday.
Yeah, Thursday.
The whole 4 today.
Thursday we have a lot of time, cause we have the regular class, and the other one. So I'm looking at around 4:04, like get through with the third law. If we could get through 4.5 today, cause we're on second law. So then if we could get through 4.5, and then
Strategy.
Tuesday we'll be able to look at some of the problems and whatnot, and hopefully get through 5 as soon as possible, and then have
5 ain't long.
yeah 5 isn't too long. So, and then we already talked about friction a little bit, drag forces, elasticity. So and then Thursday lab we'll have a lot of time, do a lot of questions, and but yeah, we can check it out. We can look at some of the conceptual and problems, some of the problems and exercises. Yep, that's cool. We'll work on that. So, talking about Newton's laws. So of course this has to do with dynamics and forces. Last class we talked about mass, inertia, understanding the first law of motion. You want to remember the first law of motion?
And after that same motion, same motion will stay in motion until force is acted upon it.
Right. And at rest.
Oh, yeah, and that rest, yeah.
Remains at rest unless acted upon.
At rest, remains at rest, in motion, remains in motion.
Yeah, unless acted upon by an external force.
Yeah, don't forget that part.
Yeah, it's once you get that first part, then it pretty much makes sense. Oh, okay. Unless it's gonna remain constant unless something happens. That's the force. So that's first law, and then it also has to do with inertia. So and then the equation that they're gonna use will come up here next. So then, Erica, which has more mass, a kilogram of cotton balls or a kilogram of gold?
No. It's same.
Oh.
No, because we answered the, or where's she gone? She was gone. I think it was me and,
Oh,
okay, so
she
I
left.
apologize. Y'all can go ahead.
Same.
Wait,
I
wait.
gotta say the gold.
Right, okay. You would think it's the gold because it has more matter.
Yeah.
It's more massive, but
Mass is like just the density. But it's some matter, but they gonna weigh the same amount.
right, if I say a kilogram of mass,
What's wrong? Is it the capital?
that's the
I'm
mass.
sorry. I'm gonna throw my water bottle on the floor.
They're equal.
Oh, okay.
Yeah, it's the kilogram.
Okay.
Yeah, some weight density. We in chemistry now. Come on now. That's all he do is run his mouth about
Yeah.
But you know what? I said it was a cotton ball, so I was
I
wrong.
don't know you lying.
Yeah, so we looked at density and we were able to see D equals M over V.
You know what? That's what it is. He was like, even though the density is different, they still want, that don't have nothing to do with the weight. So it just means that there's more tightly compact atoms and molecules inside of it, but they're gonna weigh the same thing.
Yeah, so we're about to see W equals mg. So then it has a lot to do with the gravitational acceleration. And on Earth, we know that it's 9.8 meters per second squared. All right, density, mass divided by volume. So then he was saying, well, what's mass? Like, doesn't mass have to do with density? Well, yeah, density does have to do with mass. And then what's the other thing attached to here?
Volume.
It's volume. So mass is the density times the volume. However, if I have a greater volume, my density will get lower. If I have a lower volume, then my density will get greater.
Okay,
You know.
so that would be like only having 1 brick of gold or something compared to like having like cotton balls way up to here.
Right, the volume increases, but it's less dense.
Mhm.
Exactly. When the volume increases, it's less dense. Yep. So then if my volume goes lower,
Which one
mass
is
the same.
considered the intensive or extensive?
Oh, yeah.
part?
Here, I'll write it with
That
this.
considered line?
I like these markers more.
It doesn't matter.
You know my nerves. You know my nerves.
So we're about to see how.
We was there until after 5. We was there until like 5:08. 5:10. He was like, I got stuff to do, y'all. It's like time I thought we made this experience this time. But yeah, I'm gonna start reading it.
I'm gonna start pre-planning these labs.
That's why I'm gonna even look for a video and see if somebody did the lab. So I could, when I get in there,
It takes too
have
long.
this item, I already know what to do. I don't need to read. That's the ills.
It takes too long.
So then we're about to see.
You gotta take these classes, like, you can only literally take, you should really just take one science and then like 2 little side classes, cause you gotta put all your time, you gotta put so much time up in there. And if you work
So they're in a
full-time,
relationship.
it's not going. One girl, she told me she took A and B by herself, yeah, with some class she had the whole semester, cause it's real hard.
A&P? That place ain't
No
that
way.
hard.
You know, it'll be depending on what type of school you go to. Forgot what school she went to though. I had to take that alone because she said she failed it one time, so she just took it by herself.
A&P is just a lot of memorization. That's it. If you can't remember it, you don't have it.
Yeah.
That's it.
It's technically a lower.
Anatomy and physiology, it's like mainly based on the body system or something.
Mhm.
Oh, I love the body system. It's my favorite thing in the whole wide world, guys.
So now we're about to see what F net equals, the net forces. Y'all remember talking about that?
No, no, no.
Ethnic.
Oh,
Yes, the inertia.
Y'all actually left.
I'm about to say, I don't think we got that far.
Y'all actually left.
Then we swing a baseball or something, and they had that on the picture. It was in there.
Yeah, the video,
I just can't remember
yeah.
what the word was.
Mm-hmm. So now we're about to look at a change in velocity with acceleration. So Newton's second law of motion. So we're about to look at net force, the external forces, the systems. We're about to look at Newton's second law of motion and then applying Newton's second law to determine the weight of an object. So it's closely related to Newton's first law of motion. Mathematically states the cause and effect relationship between force and changes in motion. So this is basically a quantitative way of saying how force, mass, acceleration works together. So that's all that's saying.
So is it trying to say that Newton's first law is more qualitative?
Yeah. Yeah. Exactly. But then we're about to see that it says Newton's second law. The acceleration of a system is directly proportional to and in the same direction as the net external force acting on the system and inversely proportional to its mass. All that's saying is that my acceleration is going to be in the same direction as the net external force. So we're about to look at F net equals MA. F equals MA, F equals MA, F equals MA. That's been such a big highlight to Einstein's work, is understanding F equals MA. So now, what does that mean? That what does the second part of that say? That is
What?
inversely proportional to its mass.
Where you see that at? Oh, okay.
Yeah, acceleration. So it's saying that basically F net is basically A. You know, it's definitely the same as acceleration. But it's also inversely proportional to its mass. So that's why we need to say it's inversely proportional to its mass like that. But typically, we're gonna see it like this: F net equals MA, F equals MA, F equals MA. That's typically how we see it. But second law says that it's in that acceleration. So since they're vectors, we're gonna put an arrow over it. So sometimes you'll see something with an arrow over it. That just means that it's a vector. But then we're gonna say that it's in the same direction. If F net is going that way, then A is also gonna go that way. Our net external forces are in the same direction as this acceleration.
I'm not. You have to like break.
Yeah, we'll get to it. So we know acceleration is the change in velocity. We see that net external forces cause acceleration. So Newton's first law says that a net external force causes a change in motion. Thus we see that a net external force causes acceleration. Another question immediately arises. What do we mean by an external force? An intuitive notion of external is correct. An external force acts from the outside of the system. Hey, great day. Welcome in. So an external force acts from outside the system. So we don't have to add in what the muscles of the child is in this example. We don't have to know what the muscles are, how much he's breathing, you know. Those are internal forces, internal to the system.
Okay.
You know, we constantly have forces going on in our body, like, yeah, my blood's moving, my air is coming in and going out, and I'm constantly, you know, changing internally as well.
And too, like if you're moving
My brain.
like this, well, you know, the dynamics of your body can, you know,
Yeah,
how
can
fast something is going.
right, can move, you know, I can start looking at like, oh, this bolt is here and it can move a little bit and it can turn, and you know, but we're just saying in a straight path, just only looking at external.
Okay.
You know, that's why when we do free body, we just say it's a free body. You know, it doesn't have internal forces into it. We're just looking at the motion, just looking at what's going on in a complete system rather than just internal. So, which even greater, which I remember them saying here, the internal forces actually cancel, as we'll see in the next section. So
don't even worry about it.
Yep. So here, the girl's pushing on the child is in the same direction as its acceleration. Of course, acceleration can go in the negative direction, but then the net force is still going to be in that direction. Like if it's slowing down, decelerating, A can be in the other direction, but the net force is, since it's decelerating, now I'm starting to get a net force slowing down. So anyway, we'll get to that too. So now we're about to add in another force. Miss Elise knows what that N force is now. You remember the N? So because I have this wagon onto the ground, what's making the wagon not go all the way down into the ground or going further down south?
The negative force.
It's not so much negative force. There's another name for it. I see why you say that, but there's another name for it.
What do you mean down to the ground? What do you mean by that?
It's the force of the ground that's pushing back up on the wagon.
Exactly. And that's called the normal force. It's normal too. So we're about to learn. So we got the weight of the system and the support of the ground in are also shown for completeness and are assumed to cancel.
We got a whole class to do.
Hey, great day. So we have each force. We have two forces, two children pushing on this child. This small f is going to be friction, so of course that's going to go in the other direction. So this is our free body diagram. Just a point. Your normal force is supporting the wagon, so it's going to go up, and then W is down, weight, normal force, and then there's two forces being pushed. Since we're going to look at what cancels out, so that's why they have it like this, to kind of show you this net force is going to be stronger than the force of friction, and then the normal force and weight, pretty much cancel out. It's what they're saying. But then we have a F1 and a F2, which are, one looks to be larger than the other. So, all right. So, and then we have here the force of the adult pushing. So, of course, that's going to be even greater. And then we have a F. Of course, we still have the normal and the weight. All right. So we have our vertical forces, W and N, our horizontal force representing friction, and then also the net force. So this shows how vectors representing the external forces and to add together to produce a net force. All right, so here's our big symbol for the second law. It's explaining, writing the relationship of acceleration and net external force. So acceleration is proportional to the net force. So that squiggly line in between there, that means proportional to, if you ever see that. But typically, it's going to be the equal sign, F net is the external force. The net external force is the vector sum of all external forces and can be determined graphically using the head-to-tail method or analytically using components. All right. So that's where that A is proportional to 1 over M then. Because we said we said before that it's inversely proportional to its mass. Alright. Experiments have shown that acceleration is exactly inversely proportional to mass, just as it is exactly linearly proportional to the net external force. Alright? So that's the big thing that you'll understand about Newton's second law. So this mass, pushing it, acceleration, of course I have a mass 2. My acceleration is going to be less. Putting out this force. Free body diagrams for both objects are the same. Alright. That has to do with that external force. It's been found that acceleration of an object depends only on the net external force and the mass of the object. Combining the two proportionalities just given yields Newton's second law of motion. Alright, so in equation form, Newton's second law of motion, acceleration equals F net over m. This is often written in the more familiar form, F net equals ma. When only the magnitude of force and acceleration are considered, this equation is simply F equals ma. Alright, that's the big thing. F equals ma, F equals ma. The law is a cause and effect relationship among three quantities that is not simply based on their definitions. So it's definitely valid based on our experiments. Alright, so what is the unit of force? So this N is not a normal. This doesn't say one normal force.
That's Newton, right?
Yep. And then what is a Newton?
That's the SI for,
Yeah, you're saying it right. It's Newton.
It's
The SI unit of force. Yeah, you're right. Yeah, be confident. You in there.
I remember a little bit.
Trust your gut.
Yeah.
Trust your gut. Alright, so it's a kg m over s squared. 1 kilogram, how much it accelerates is able to accelerate 1 kilogram. So 1 kilogram times meter per second squared. So how much is 0.225 pounds? How much is 0.2 pounds?
What, Newtons?
It says 1 Newton is around 0.2 pounds. Is there something similar that equals about 0.2 pounds? There's something that I was watching another video and they were explaining what a Newton may be on Earth, what that weight may be. Anybody have a guess? How much? You said an atom?
Well, I'm saying like, what did you want to know a number and not?
Like an item, an object, something that might be 0.25 pounds, 0.22 pounds.
I don't know, a pea. I don't know.
A pea?
Broccoli.
Broccoli?
Broccoli.
Those are good guesses. So they said that an apple, a smaller apple, would be about the same size as a Newton.
Okay.
Yeah. So this one might be. They said a typical apple. This apple might be a little bit bigger.
That's a big apple.
It's probably like a half pound.
That's a big apple.
Yeah, this came from the farmer's market.
Oh, okay.
They don't put all that extra stuff. But yeah, they say an apple is about the weight that you feel on Earth as a Newton. I say on Earth, as you'll see later, right here. Alright, so now we're talking about weight and the gravitational force. So this is important because gravity changes on different areas. But it's accelerating toward the center of Earth. So we know weight is actually going to be a downward force. Alright? Which means that it can be a vector too, huh? right? So the magnitude of weight is denoted as W, but we also know it's a direction, and it's got to be down. Galileo was instrumental in showing that in the absence of air resistance, like we saw last class, or 2 classes ago, all objects fall with the same acceleration g. Using Galileo's result and Newton's second law, we can derive an equation for weight. So what is that? We just looked at it. W equals mg. So here it says, since the object experiences only the downward force of gravity, F net equals W. We know that the acceleration of an object due to gravity is g, or A equals g, substituting these. So that's why you see F net equals W. So it's basically the same. So W equals F net. And then you'll see F net must equal mg. Let's make that a different color so it doesn't look confusing.
What is on your mind? G stands for gravity.
Yeah, so that's why you'll see F equals ma. You also see, because weight equals mass times gravity. So you'll see here, this is the equation for weight. W equals mg. Alright. Since g is 9.8 meters per second squared on Earth, the weight of a 1 kilogram object on Earth is 9.8 newtons. So in reality, when we go to the doctor's office or step on a scale, we should actually be saying that we're in newtons. We should actually be looking at newtons for weight. We see here weight is newtons. When we do our W equals mg, our mass is kilogram. Our key is m over second squared. So our weight is actually supposed to be in newtons. Got a question?
So for this part, is the gravity always going to be positive in the positive part? Yeah.
Yeah, it would be nice to say negative, but it would be negative. But if we just want to say what the weight is, then yeah, we just keep it as positive. Like it says here, recall that G can take a positive or negative value depending on the positive direction in the coordinate system. Be sure to take this into consideration. So, yeah, that's a good point, but we'll look at that a little later. Doesn't really. We typically don't give quantities a negative weight.
Okay.
That's one of the reasons. That's one of the reasons why we should just keep it positive. Or much like a vector, if I just say how fast it's going, I typically, it's accelerating, but I would typically just, even if I'm going backwards, like reversing, if I just want the number of how fast I'm going, then I would just keep it positive. Alright, good question. We'll look at that a little later. Alright, when the net external force on an object is its weight, we say that it is in free fall. That is, the only force acting on the object is the force of gravity. In the real world, when objects fall downward toward Earth, they are never truly